Hello, and thanks for joining our conversation today. There are few topics as exciting and scary as humanoid robots. Humanoid robots are meant to assist and in some cases replace humans. Because of the ergonomics, they are shaped like humans with legs, arms, feet, hands, etc. They also look like humans for comfort, although that familiarity varies by region. Michael, give us an idea of the humanoid robot market.
Sure. So the humanoid robot market, as you mentioned in your introduction, is a very exciting one. We're seeing almost daily news headlines coming out about this application and these robotics, and there's lots of excitement, as mentioned. So we're seeing robots competing in boxing competitions, folding clothes, doing various industrial tasks like in warehouses and factories. And so the Bank of America Institute, it projected the growth of these robots in 3 stages. And right now we'd be in their first stage, which is the development stage, which is projected to take place until and through 2027, which really is about robots doing semi-structured or tasks in semi-structured environments, industrial production and logistics, material handling and sorting. The next stage would be from 2028 to 2034, and that's when we're seeing an increase in adoption, especially in education and business services, specifically less structured environments here. So robotics are becoming more flexible and more capable of doing more complex tasks, and also real-time interaction with humans, which would be a giant leap forward. And then the third and final stage would be from 2035 onward, and that's really when the volume of these robots starts to take off, and that's when they start to be adopted into households with mass adoption for all. The qualifier here is highly unstructured working environments. In households, smooth interaction with humans, and also the key here is that affordable production costs. So right now, one of the big drawbacks of these robots is that the bill of materials costs, what it takes to produce these robots and design them, is very high. So what will need to happen in order for the volume to increase for these robots is that the bill of materials cost and the components general production cost starts to come down on these.
Thank you, Michael. What an interesting market. Kyle, to design a complete humanoid robot is very complex. Tell us about some of the complexity and how our companies are addressing it.
Thank you. Humanoid robots vary very much between purposes and regions. Some examples that you have are whether the humanoid robot is meant to be acting as an acrobatic versus, a long-distance runner, or just meant to be carrying out industrial-type tasks. So you have your examples of, Tiangong's Ultra that ran the half marathon over in China. You also have Unitri's G1. You have Noetic's N2. Kind of more in the Western market, you have, Boston Dynamics Atlas. So these kind of differ between each other. And then you also have to consider something like, springing and bounding, like, your acrobatic robots versus your continuous movements. So the North American market is kind of more focused on your industrial tasks or more for the household. You kind of have more in China is more about, your mass production or kind of domestic tasks. Korea and Japan, you kind of have more of a social, more interactive type of robot. And then, Europe, you kind of see more, your workplace collaboration between humans and robots at the same time within the industry. With each purpose or market, you have these different needs that appear. And so it's important to really decide which pieces of hardware do you need. Do you need additional pieces in, your face, your body, wherever it may be? And then where is it located? It might change depending on your market. Not to mention that if you have different pieces of hardware, you have to worry about how they interface with one another. And lastly, some of the more typical features become unnecessary, and some less common features sometimes become critical.
Thank you, Kyle. At Hirose, we study this market working with customers and talking to local universities. This is a very exciting and challenging future, so we want to be ready for it and anticipate it. The humanoid robotic industry is growing and evolving just like the automotive and personal computer did. Hirose has been around for more than 80 years, so we have witnessed this type of transformation. There will be an ecosystem of hundreds, thousands of small, medium, and large companies working together to create humanoid robots. Some companies will specialize in components or subassemblies like feet, hand, torso, etc. Interoperability is going to be key so that all these components could work together. Mechanical and electrical interfaces will have to be defined, and so protocols for communication. This webinar will focus on connectivity because the integration of thousands of components by multiple companies will require that. We will arbitrarily divide the humanoid robot into 4 sections: the head, upper extremities, lower body, and torso. And just like humans, a robot needs a good head on their shoulders, so we're going to start with the head. Kyle, a humanoid robot needs to hear, to listen, speak. What are the main components in the head?
Well, let me just say that the head is the most elevated location of the robot. So you typically have your awareness devices on the top of the head. So the head can typically consist of your cameras and your LiDARs. That helps kind of give you spatial awareness. And then it also tends to have microphones or speakers. That's kind of your communication aspect.
And Kyle, when do we have cameras or LiDARs?
Well, cameras and LiDARs serve different purposes. They kind of collect data differently. So LiDAR stands for light detection and ranging. What it typically does is it shoots small light pulses, and then the time it takes for that light pulse to return helps determine the distance of that light ray. Cameras are kind of more familiar to people. You capture your rich visual data. So when would you use one over the other? Well, LiDAR doesn't require external lighting. So you don't have to use any of your power consumption to have some sort of light source on the robot. You don't have to have an ambient room or environment in which there's lighting. On top of that, LiDAR collects cloud data. So it kind of helps you see almost a plane and map out the environment. So it's great for spatial environmental detection and awareness. Some of the downsides of LiDAR is that it can struggle with transparent or reflective materials such as glass or a mirror or something else that's see-through like a clear plastic or something like that. And then also LiDAR cannot provide any color data. It doesn't provide any texture data. It is 100% just distance. As for a camera, it gives you your high-resolution imagery. So it's more useful if you're looking for something that is lightweight, maybe a little bit less expensive. Some of the downsides that you have with cameras is that it degrades with a low light, or if you have high light and it glares off of something, you kind of have a degrade of the resolution of your image. Both are extremely common in a single system, but not every system uses both of them.
So we probably see a combination of both. Mark, what challenges and solutions we have for cameras?
Yeah, let's focus on that, since I think we'd all agree cameras are going to be the highest data rate types of transmission elements up there in the head that Kyle was just talking about. And they're also probably in a humanoid robot we see going to be having to get down to the central processing platform within the robot, which is probably going to be down more in the torso. So you have some decent cable lengths as well, which simply adds a little bit more challenge. The kinds of high resolution camera standards that we're seeing show up not only in humanoid robots, but many other applications would cover things like MIPI, MIPI-C, MIPI-D, EDP, electronic display port, or it could be proprietary differential signaling as well. But any of these are going to be at least in the 5 to 10 gigabit per second data rate range. And so therefore, they're going to require some care in choosing your connector cabling solutions. The good news is that there's some, the connector world and cabling world are keeping up nicely with these types of requirements. And there's a couple of different options that we're actually seeing larger humanoid robot OEMs pursue. The first would be to use something like this, which is a flexible printed circuit cable. Flexible printed circuit cables is a very mature technology. It's pretty low cost, and the length of that cable run can really be tailored to whatever the application requires. From the connector endpoint or termination standpoint, a couple different options, and actually the sample I have here would be one of those often referred to as a ZIF or zero insertion force, and it's really a one-piece connector, so you don't really need anything on the end of the little flexible printed circuit. It just goes directly into this connector, and then it closes with a lever. The other option, and this is a little smaller, so sorry if it's harder to see, the other option would still use the same type of FPC material for the cable, but in this case, it's a two-piece connector solution with one half of the connector SMT'd onto the FPC itself, and the other half of the connector pair SMT'd onto the PCB substrate, which could be a sensor board inside the camera, or it could be the processing board down in the torso. In this case, obviously, you're going to snap these two, and again, maybe you can't see that very well, but you're going to snap the two pieces together. So FPC solutions are going to come into play. One other limitation that should be clear and be made up front is that an FPC, by virtue of being a two-dimensional cable, bends very nicely in one dimension, but really doesn't bend at all in the other. How people and designers get around that is some origami type folding to some limitations for the tolerances of the bend radiuses of the cable can certainly be applied, and that's often is done in articulated types of arms. Certainly humanoid robots would be a good candidate for that. But it's a tried and true cabling and connector solution that a lot of folks are quite comfortable with already. There is another family of products that would take the signal integrity up a notch. It's going to be a little more expensive solution, but again, a lot of design engineers are very comfortable with microcoax. Microcoax is just what it sounds like. It's a very, very tiny, down to sub-millimeter pitch from one to the next, bonded substrate of many coaxial cables. These are all terminated together to a similar single-piece connector. And again, if you look at this demo I'm holding in my hand, it looks similar to the ribbon cable I just showed as the FPC. But the difference, one difference on this is that the cables could easily be debonded and treated as a bundled core. Now you have a very flexible single core of bundled wires that can be articulated through joints repeatedly with much more flexibility, with much more degrees of freedom than a true permanent 2D substrate such as an FPC. The other benefit that these bring is just inherently by their nature, the microcoax connectors are individually shielded. Each of those individual transmission lines is by definition individually shielded. So your signal integrity is going to be maybe arguably an order of magnitude greater in capability. These could easily handle up to 10, 20 gigabits per second. Could also route analog RF types of signals through them as well, which microcoax, of course, or any type of coax cable is very well intended for. So those are two primary families of solutions that we'd see being used, and we'd recommend anybody looking into a humanoid robot camera type of application would be the FPCs and the ganged microcoaxes.
If I can also ask Mark a question here, I'm curious. Mark, which is more flexible, the ganged microcoax or the FXC or FPC?
Well, just by virtue of the fact that the gang microcoax can be unbonded and treated as a bundled core of discrete cables, I think that's clear that one would now be almost unlimited again, to the degree of the bend radius comes into play, would be unlimited in 3 dimensions of where and how you can articulate that cable. So certainly if that routing of the cable in 3 dimensions is a key challenge for a humanoid robot designer, that more expensive but more flexible and higher signal integrity solution of the microcoax could be one.
Mark, as you mentioned, signal integrity and high speeds are very important. Michael, how about optical solutions?
Yeah, exactly. And that's what I was thinking about, because it seems like Mark himself kind of built a spectrum here, starting with FFC and FPC, going to microcoax, the spectrum being based off of signal integrity and also flexibility. I think that leads very well into our optical solutions, which we're seeing some interest in, especially when the robot has to be, once it's getting to those more complex tasks and when flexibility is more of a demand and wire bendability becomes more of a necessity. So what we have that we've seen from robotics customers, whether it's medical robots or even some very dynamic humanoid robots, is what we call our active optical solutions, where on a plug harness and a receptacle, On the transmission side, this is what active optical means. On the transmission side, you have a chip that converts an electrical signal into an optical one, and then that gets transmitted through the fiber at a fast data rate of, right now we have 6.25 gigabits per second. And then on the receiving side, the signal gets converted back into an electrical signal. The signal gets converted back into an electrical one on the receive side. And so this connectivity is also inspired based off of electrical connectivity too. So you're able to harness the benefits of optical with an electrical type operation. And so what that means, I mentioned 6.25 gigabits per second. Of course, with optical solutions, you also have virtually noise-free. And then we also have a next generation version of this coming out at 12.5 gigabits per second. So whether this is imaging, cameras in the head being routed to the chest, torso area, or it's AI processing, whatever the case is, this is a very good and compelling solution for those more demanding robotics applications.
So in this case, the mating of the connectors is done electrically and not optically, so that's immune to dust. So that's good. Michael, tell us about some of the challenges and solutions for LiDAR.
So there's a couple things to mention here. One of them is the challenge of just a robust, small space-saving, high-speed transmitting input-output connector. I am going to get to those a bit later at a later section, but I'll just mention a couple right away. And one of them is our iX industrial connector, which we developed in the mid-2010s. This is originally marketed as a replacement for the RJ45 connector, so it's 75% smaller than the RJ45. It has better shielding. It's 360 degrees shielding. And if you have an RJ45 that's mateable at about 400 or 500 times at a maximum for the RJ45, the iX Industrial is rated for 5,000 mating cycles. It's also more robust. It was tested on high-speed bullet trains. Most of us have the issue with the RJ45. We've probably broken some of these connectors before. The iX is less likely to have that problem. Also, with input-output connectivity for LiDAR, we have just your regular USB done in the Hirose fashion with very good tactile feel and board retention with over 30 variations of it. But then we also have an automotive rated USB-C, which we call our AU1, and that has a CPA feature on it, which is a connector position assurance. It's a form of a secondary lock and brings in that automotive connectivity benefit to the application. And so when you're talking about LiDAR, of course, strong use in automotive. So this is a good time to talk about, and many robotics engineers probably are already doing this, looking for automotive connectivity, but with LiDARs, you can get that in wire-to-board or board-to-board fashion. So automotive connectivity is primarily about resistance to shock and vibration, and then there's also an operating temperature component too. So I'm seeing humanoid robots these days, 85 degrees Celsius at an upper range in the operating temperature is sufficient, but maybe as time moves along, we'll start to see more demands for higher operating temperatures. But so I mentioned that the USB-C for automotive has a secondary lock type or a secondary locking feature. There's also board-to-board, so we're seeing shielding board-to-boards. We're seeing a floating feature in the design of board-to-boards, which is helpful for automated assembly, and also a misalignment absorption technology, which is what floating is. And then also these board-to-boards that are capable of transmitting data at 16 gigabits per second and with support for protocols like PCIe and MIPI. So this is some of those things that we can bring to the table with LiDAR connectivity. And with wire-to-board, the last one that I'll mention, we have something called the GT50, which again is a very small wire-to-board connector with a 1 millimeter pitch that we're finding came out of the automotive space and is starting to have interest in the humanoid robot space as well.
Thank you, Michael. We talk about cameras and LiDARs. Kyle, any other components in the head?
Well, I mentioned earlier that features can differ depending on the region. So the first thing that comes to mind is kind of your screen, whether that's an LCD or OLED screen. I would say that this is more used for communication or some sort of human interaction. It's more common in the kind of Korean or Japanese markets, but it might be a way to show kind of information such as text or emoticons, something like that. You also see sometimes motors for facial movement. This is typically more for the humanoid robots that want to show off the humanoid head rather than the other functions such as limb movement or, hand grippers. I see this most commonly used if a company is trying to show off their AI rather than just the humanoid robot itself. And it takes up a decent amount of space in order to put all those motors in there. So you might be sacrificing incoming information such as camera data or LiDAR information. Another thing that you might see in the head is indicator lights. So this might be, a blinking light to indicate a heartbeat or Wi-Fi signal, maybe just the fact that it's powered on. You might see this here. As well as, maybe a yellow light or blinking, blue light for processing that's going on within the body itself.
Thank you, Kyle. Let's move down to the lower body. Kyle, what are the challenges there?
The leg holds up the robot off the ground. It allows it to be mobile. So in that case, balance is critical for static and dynamic movements. Movement over various obstacles or changing environments is extremely crucial, whether you're in shallow water, whether you're stepping over objects. That's very important when you talk about the balance of the legs. So if you were to lift an object, if it's heavy or light, it's going to resist the motor or the actuator within the legs. So the motors have to apply a greater force if it's heavier, and if you're going to do that, you're not going to move as quickly. So now you're talking about lower speeds, you're talking about a higher torque that typically involves either a geared motor or its own gearbox. And then on top of that, the robot itself has to kind of align itself differently in preparation to lift heavier objects. And this is now where you start talking about, memory learning or, AI learning. Some of the solutions that you might have, you'll probably have a lot of sensors in order to give you data in order to react to the environment. So you'll probably have a sensor for pressure. You'll probably have a sensor for acceleration, like an accelerometer or something. You'll probably have a sensor for rotation. Some of the concerns that you might have within the legs is that robots can fall. We've seen plenty of bloopers online of robots falling over. You hear that loud crack and you're worried about damage. So you need to be able to handle, shock, which was brought up a little bit earlier for, kind of like a automotive connector, your shock and vibration. On top of that, the legs are meant to bend and shift. They're very active. So you need to think of a wiring solution that can handle cable strain and also tension for when it's straightened all the way.
Also, just to emphasize that point, because you're talking about stability. So I read that there's a group that's developing new standards for humanoid robots, safety standards, and they said that the biggest safety concern is physical stability for humanoid robots. So humanoid robots falling in a warehouse or falling in a factory is a big concern. So it's good that you're talking about this.
You talk about sensors, actuators. How do you connect all of them?
It's difficult to give a straight answer because there's a lot of solutions. So Mark was kind of bringing up earlier, you have your discrete wires. I'd say that's probably the most prevalent solution that I've seen, just getting signals or power from point A to point B. It was mentioned a little bit earlier that your larger wire gauges can kind of struggle to bend, typically because it's a proportion to the outer diameter of the insulation. So if you have power, it's not going to be able to bend as easily. If you have signal, maybe it'll still be able to bend pretty easy, maybe not as much as like a micro-coax connector. You do have solutions of using something like an FFC or an FPC. I've seen, some of those FFC cables go as long as 10 feet. So it can wire pretty far distances. And on top of that, it allows for far greater, flexibility than your standard discrete wire. But I've also seen problems where it can suffer from retention strength or it can struggle to pass some of your higher power requirements. As mentioned before, we have some optical connectors. So, those wires are able to kind of bend quite a lot and, whether it's tension or torsion, so it can handle, twists in your loops. And then another thing that you need to pay attention to is there's not unlimited space. So whether your panel is, kind of right up against your motor or your board, you need to think about your mounting orientation of the connector. So whether that is coming straight up off of your board, whether that is angled to be parallel with your board, that's exceptionally important, especially when it comes to your bending radius for your wires. Another thing that you need to think about is waterproofing. I mean, you might not need it to go underwater like some sort of submarine, but you might need to be worried about, a misting environment or, water droplets. Or maybe it is going outdoors and you're planning on handling, hurricane weather. I don't know. But you need to be able to think about waterproofing as well. And there are several solutions, whether you need it, IP24, 4X, IP67, IP68, maybe even IP69K. And there's plenty of solutions out there for that, such as, your classic circular connectors. Maybe you want a motor connector that can handle shock and vibration, something like our MT50W series. Hirose covers a large range of solutions. I think it's important to kind of go to someone like, myself or any other panelists that we have here for dedicated support and help kind of by a case-by-case situation.
Yes, Kyle, as you said, there's different solutions because there are multiple type of architectures and all of them can accomplish the same. Mark, what are some of the challenges and solutions we have for sensors and actuators?
Well, if we're segueing into the lower body, I think it's a great point to also segue into power delivery, which in the humanoid robots and robotic applications in general, we certainly see as a huge required focus for these designers to handle. I come a little bit more from the microconnector world, so let me start by introducing some options that exist for both these types of connectors I already showed, both whether it's the SMT two-pair connection type or if it's the single type that goes directly into an FPC. For both those families of products over the last few years, we've begun pretty aggressively adding power rails integrated right into those same small form factor connectors. So for instance, you might have a 2 to 100 signal pin connector, all within the form factor of a few millimeters of length of a double row 0.3 or 0.35 millimeter pitch architecture. But on the two ends of those little tiny connectors, we've actually added as beefy as possible metallized power rails. And those power rails can typically handle from 3 amps to 5 amps to 10 amps, even up to 20 amps per end cap. So a 20 amp forward and a 20 amp return is available in more than one of these tiny connector families today. Of course, we recognize that even 5, 10, or 20 amps may be far short of the power that's required for some of these heavier duty actuators. But that is nevertheless a very interesting combination that is available to any designer considering how they want to architect their humanoid robot, is taking advantage of very small and relatively low cost connector solutions that are now adding, at least for their size, a pretty significant amount of power distribution. Another, still in the small, micro/small world of connector solutions, would be discrete wire to board, which we haven't really dived into. And I just want to add, we see large humanoid robot OEM customers who are actually choosing to go with those small board to wire, not micro coax, just discrete board to wire solutions for not only their power, but their signaling. But back to power. For those very small 1 millimeter stack height, down to 0.5 millimeter pitch discrete board to wires. We offer a whole family of different types of mating mechanisms, vertical pop-in connectors, horizontal slide-in connectors, levered connectors, and all of these would come in a very small gauge of wire. So again, they're not going to offer you a lot of power, but they do offer you the ability to mix signaling and power in a pure discrete wire package.
And I think it's important just to spend time on cable management, because when I visited a robotics tech show, I spoke to one manufacturer. He owns a company, and he said that one of their biggest pain points is cable management when a robot has to be pulled out of its deployment because of a cable issue or a cable damage type of issue, and 6 hours of labor time has to be spent just servicing that issue. So this is a true pain point in robotics systems, as the robotics engineers online will know this. So with current branching adapters, we have a couple that we're talking about a lot now. So let's say that you have on a power distribution board, a board to wire connector that's taking 3 amps from the board. You can route that, input it into an adapter that can then take that 3 amps and branch out 1.5 amps to 2 different sensors. So it's a 1 input, 2 output adapter. So you can already start to see the benefits that can come. You're reducing the amount of wire that's needed, because if you had both of those sensors connecting back individually to the board, there's more wires, there's more connection spots. If you have one board-to-wire connector on the board, on the power distribution board, and it's handling the powering of six different sensors throughout the robotic system, and let's say you have an issue with the third sensor, the cable was damaged or whatever it might be, and then you have to go service just that third sensor, that's a hassle. You have to go and find the wires associated with the third sensor, take those out and try to repair it. And we see, because of all of the sensors and actuators that Kyle and Mark are talking about here, those branch adapters are quite something to pay attention to. And so we have two of them, as I mentioned. One of them fits into our DF51 series. The DF51 is there's lots of varieties to the DF51. It supports wire gauges from 22 to 30, which is a pretty large range of wire gauges. So we have a branch adapter for that series, and that's 2 millimeter pitch. But then we also, on the power end of things, when you're routing larger power, it falls into our DF22. We have an adapter for that, and that's our 7.96 millimeter pitch wire-to-board connector that's capable of up to 30 amps per pin. So these are where these branch adapters are falling in the lineup, and we think it's good when you're talking about connecting all of these peripherals, sensors, actuators, all back to the same source.
Let's go to the upper extremities, which consist of the arms and hands or grippers. Kyle, what are some of the challenges there?
Well, the arms move quickly. So in terms of how much weight is associated with them, if you're trying to pick something up quickly, or you're trying to swing a golf club, any of that upper body movement, the weight kind of changes the balance of the robot drastically. So typically when you're talking about, your wiring or your interconnects, you're talking about, how much weight is it adding, how much space is in there. And then on top of that, probably one of the most talked about topics is the hand on the arm of the robot. And the hands themselves require so much, dexterity and accuracy that you typically see a lot of additive features in order to try and counteract the problems within the dexterity or accuracy of the hand itself.
Thank you very much, Kyle. Michael, what solutions do we have there?
Yeah, I'm going to pick right back up from where Kyle was talking about. He covered some of the things that I want to talk about too. So good job, Kyle. But one of the large humanoid robot makers said that the hands account for almost 20% of the cost. They said more than half of the complexity in a humanoid robot is in the hands. So what Kyle's talking about with this small space, but highly complex space, so much of the design challenge is probably located right here in the hands. And so Kyle talked about some of those fine wire gauge micro wire-to-board connectors. I'll pick back up with saying that here there's a couple of things that you have to kind of juggle. So you want fine pitch. We have down to 0.6 millimeters. We have 0.8 millimeters. We have 1 millimeter, and in between 1 and 2 millimeters. And in that range, you have like the 0.6 millimeter, it doesn't have a positive lock on it. So it's a friction lock. So maybe your retention is less, but you're gaining that space. You go up to like a 1 millimeter pitch, and then all of a sudden you have a positive lock structure. You might also have a stronger board retention, which is a big issue. So we're seeing that mating retention is a challenge in these tiny connectors, and then also board retention as well. So we encourage you to try Hirose solutions, because we think that we do a good job here. We have a loaner tool program, so we can loan a hand tool out to you for a month or sometimes as long as you need it. We also have a wire termination program where we can give terminated wire samples of these wire-to-board connectors that we did right here in the lab to you, so that you can get started testing these connectors to see if they work in your system, because this is a demanding part of the application. The last thing that I'll talk about here, because we do see it in more of the grippers, so less the human hand, but more in the grippers, is we talked about floating board-to-board connectors that come from that automotive space. We're seeing those connectors come back here, so board-to-board that are especially hybrid connectors. So floating board-to-board hybrid, because you're saving space. That hybrid power and signal, instead of having two different connectors for one or two different for power or signal, that can be brought into one connector form where both of those things are handled in the pin layout. So in the humanoid hand, you have tactile feel sensors, you have small motors, motor encoders, and so that's what these different things are connecting in that space, and that's why it's a complex task. But do look into, because there's a lot on the market and in Hirose's catalog that we think can can help you with those challenges.
Michael, achieving human dexterity is very complex. That's why companies need to choose the level of dexterity and the functions they need to achieve. Mark, anything else to add?
Yeah, let me just take the small form factor to another level. Michael mentioned on the small board, the wires down to sub-millimeter, 0.6 pitch. Hirose has been a really trusted supplier for the very smallest consumer electronics customers for many, many years. And those types of customers are always pushing us to deliver more ruggedized, even smaller form factor capabilities. And so some of the very smallest would be back to the same FPC type family of products that I've already shared. But if we take those down to the extreme, we're talking not about 0.6 millimeter pitches, but down to 0.35, 0.3, and even a staggered contact structure that effectively accommodates 0.175 millimeter pitches. So these are connectors that are going to be very well suited for, something like a humanoid robotic hand application, where and if the space constraint is a driving design consideration. And in fact, even the sample that I just grabbed for this webinar today is a good example where with these SMT connector designs onto an FPC, you don't have to have the FPC coming out at right angles to the connector. You can actually design, just like this one has been done, to have a very thin FPC with those traces routed down the length, directly down the length of the cable. So you're really minimizing the overall package and size constraint. And just to throw in again, a reminder that even in this small form factor, we're still offering solutions that would have some level of power for maybe some minimal actuator controls of up to 3, 5, or 10 amps in addition to the signal contacts down to those tiny pitch sizes. So the entire connector in these cases could be as small as 1.2 millimeters in overall width, depending on how many signal pins you require, down to easily 3 to 4 millimeters in overall length. So these are really small connectors that nevertheless are ruggedized. Another ruggedization feature that we are driven to by our largest customers and have addressed is bringing full armored design to both pairs of connectors. That means anywhere where these tiny connectors are being mated in high volume, there's no plastic on plastic contact, there's no plastic on metal contact, only 100% metal on metal contact. And that's because we've simply added metal structures on every point of each of the pairs of connectors that mate. And that's a big issue because in high volume manufacturing and assembly, these tiny structures are very prone to breakage. So having metal on metal structures only really mitigates largely that requirement. And I'm just going to throw in one more feature that we haven't really, I think I mentioned it just in passing, but one more interesting feature that again applies to the very same connectors, again, the small board to FPC style, and that is the integrated shield options. In fact, the connector I'm holding is one of our newer solutions that does do just that. And for an engineer, my great analogy I love to use is the analogy of integrating a shield box, which any engineer's probably seen shield boxes covering areas of components or individual components on a PCB substrate to mitigate that EMI noise. Many engineers we see are just so quickly appreciative, and want to be able to utilize that additional signaling EMI mitigation of having an integrated shield structure, that we're really seeing a lot of pull from the industry for using those types of solutions. So those are just a couple of new other aspects I'd add when we're talking about those dexterous hand types of applications from the small connector standpoint.
Mark, in summary, adding metals to connector achieves 3 functions. Number 1, makes the connectors more rugged. Number 2, helps with signal integrity by shielding. And number 3, it helps transmit more power. Let's move to the last section, the torso. Kyle, what are the main functions and components there?
Well, the torso is the heart of the computation and the power. So you'll likely see, your battery source here. You'll likely see your CPU, your processing, your power distribution to go to every other component probably comes from the torso. So we're expecting multiple different PCBs. All of these have to transmit either signal or power, or the most likely case, both. So if you're having, your main, I'll call it a motherboard, and you have all your daughter cards or your hats, your little boards that are kind of connecting off of the main board. You're bringing wires away from all of those in order to connect all of them. Some of them will be connected through kind of your larger board-to-board solutions. On top of that, we also see a lot of times that the power that comes off of these boards, you need it to kind of be parallel to the board. You need it to be able to route the wires from the center and not from the end off towards a different PCB. So something like our SnapBeak collection might be very useful because you're able to kind of press it down vertically and insert it, but the wires are still parallel to the PCB. And those wires are just lifted off the PCB enough to where you could route it over, such as your resistors, your capacitors, your ICs.
For the purpose of this webinar, we're going to define I/O as communication among these sections. Michael, what solution do we have for that?
So I talked about the iX Industrial, which was that originally promoted as a replacement for the RJ45. One other thing that I'll mention about it here is that it has 3 different keyings, one for Ethernet and one also for non-Ethernet, and then a third one. So we're also seeing, especially in robotic systems and just for general purpose I/O, as a robust and small I/O with many mating cycles, that it's being used even for non-Ethernet purposes. I mentioned that automotive grade USB-C. Other thing that I'll mention is that we have input-output connectors in a circular type of form with easy-to-operate locking structures. They're not twist type of connectors, but they might be push-on bayonet style where all you have to do is just push it in. It might be a quarter-turn bayonet lock, like a traditional bayonet locking connector. And these sometimes are, again, hybrid in power. Oftentimes they're rated to Cat 6A Ethernet, like our LF series, or Cat 5e Ethernet, like our HR30, or a separate variation of the LF series. So looking for what can pass the data rate, what's robust, what's easy to use. These are primary features of a quality input-output connector for the application.
Thank you, Michael. Mark, Kyle talked about computational analysis earlier. What challenges and solutions do you see there?
Humanoid robot designers are likely following some of the large silicon platforms supporting those, GPU, CPU-based platforms. In those cases, the connectorization might already be defined, by those suppliers. Hirose is actually quite involved in that world. We're one of the suppliers of the OCP Open Compute Platform standardized connector solution for going, just as Kyle mentioned, from a motherboard to a GPU. We also have a related family of high-speed products. And for these types of products, we're talking about, many hundreds of differential pairs on a single array type 2-dimensional substrate board-to-board connector, which again might be a very thin connector, still as thin as 1.5 millimeter stack height, or it could be significantly taller based on the requirements of that architecture. So we have a variety of those, and these are, as far as bandwidth goes or data rates, we're talking about PCI Gen 6 and beyond. So these are quite high data rates that are being supported by these types of connectivities. Some designers may not be following a industry or OEM standard GPU type platform, but doing their own FPGA or dedicated processor platforms for their motherboard design. So we do have a range of proprietary solutions where they might find a better fit for just what they're looking at. I'll just repeat the mention of floating connectivity. One sort of rule of thumb to keep in mind if you're wondering whether you really need to go down that route is, do you have more than one hard connectorization between a single sandwiched motherboard and daughter board? If you have one connectorization, well, you're going to be able to inherently accommodate some tolerances on the placement of those two connectors. But if you have any more than that, if you have two rigid connectors between two rigid substrates, suddenly the tolerances become a exponentially more important issue to address. And that's where having at least one of those connectors be a floating connector can easily mitigate those issues. And we're pushing floating connectors because they're popular from these larger form factors that you might imagine would be used for these types of large boards, down to, again, quite small form factors where the floating active mechanism of floating has been designed into a connector with a stack up of as small as 3 millimeters and a signal pitch of 0.4 millimeters. So you can actually enjoy the benefits of some of these floating capabilities even down into the smaller, if not micro, at least very small connector form factors. So from the central processing platform, those are some of the points I would make.
Yeah, and the presence of AI is going to be very important. AI is needed so that the robots can interface with the world and have to learn quickly. As humans, we have the advantage of learning over many years, but humanoid robots don't have that. Computational analysis and power are going to be very important. Michael, can you comment about power needs, power distribution, and power in general?
So I'll start with the battery management system here because I think we have a really good offering that I want to talk about right away. And that's with a new connector category for us. It's what we're calling like a two-piece flex. It's also like a positive lock flex connector. So it's more of a combination that falls somewhere between discrete wire-type wire-to-board connectivity and FFC or FPC, because the cable is FPC, but the header side actually is like a discrete wire with a positive lock on it that's very easy to operate. And so you're able to harness the benefits of a flex connector while the robust and reliability and easy operability of an FFC or FPC connector. So this comes from automotive. So when we're talking about connecting the battery cells to the battery management system, this is a good option there. The voltage rating is 100 volts AC/DC. And again, it's that positive lock, and this is a good option for connecting the battery management system. And then I will also mention, because we've talked about larger gauge wire-to-board connectors that are capable of 30 amps, 45 amps, maybe even up to 60 or 65 amps per pin. One thing we didn't mention yet is a board-to-board option. So we're also seeing where board-to-boards can come into play here. So there's one of Hirose's connectors called the FX30B, and that's between 13 and 25 amps per pin, I think between 2 and 5 or 6 positions in orientations of a parallel, coplanar, or a right angle. So depending on what your orientation is and how your power design is looking inside, this could also come in handy here.
Thank you, Michael. That was very interesting. This is such a fascinating and complex topic. We're just touching the surface of humanoid robots. This concludes this webinar today, and now we are going to go to the Q&A section.